Welcome to Let's Talk, a podcast series by the Undergraduate Laboratories Electrochemical Safety Research Institute. My name is Daniel, and I will be your host for this episode. In the Let's Talk series, we host discussions with leading experts, scientists, and engineers from around the world in energy storage systems, safety science, and standards, and learn about their experiences and visions through the perspectives they share. Today, our discussion will be centered on an industrial research career in the energy storage field. To understand a little more about the advantages of working in each area and help young people decide which is the best option for them, our guest today is Steve Harris. Dr. Steve Harris received a bachelor's degree in chemistry from UCLA and a PhD in physical chemistry from Harvard University in 1975. Steve worked at GM for 21 years until 2011. Since then, he has worked in the Material Science Division at Lawrence Berkeley Lab for 7 years, and he's presently a visiting scholar in the Material Science and Engineering Department at Stanford. Steve, welcome to our podcast.
Thank you very much.
Before we start the talk, I want to give a few backgrounds. A few years ago, when I was a PhD student, I came across with a PowerPoint presentation that precisely summarized the differences between working in industry and academia. I wish I had that document when I started college. So what motivated you to write this document?
There's very little general purpose mentoring that goes on in universities other than professors showing grad students what it's like to be a professor. There's not much information about industrial careers available either to the professors or the students. So I just wanted to share my experience. I love talking to students. One of the things I missed in an industrial career is I didn't really have very much contact with students, and I missed that. And so this is an opportunity for me to talk to smart young students, young people in earlier in their careers, hear things that maybe you don't always hear from people my age.
Mm-hmm. And do you think this presentation can be extrapolated to other fields, like let's say someone from physics, math, astronomy, law?
So I think my experience in industry, in principle, could be applied to most other fields, except that I worked in large companies that had central research laboratories. And most of those central research laboratories either don't exist anymore or they are scaled way back. So some parts of my experience just don't exist anymore. On the other hand, sort of the political nature of how to survive and thrive in industry are, I think, sort of universally true. For example, in industry, you're part of a team, and you're expected to work on what your supervisors tell you to work on. Those are sort of universal, I think, and it doesn't matter whether you're working for a small company or a big company.
Mm-hmm. So I would like to go back like a few years when you were a student. How did you get interested in research? Was it a natural process? Like it was a dream you already had, or it was something that you learned in grad school?
Well, my father was a mathematician. And so I grew up with the idea that I was going to be a research scientist, even when I was very young. And I just sort of plowed through for 15 minutes when I was maybe a freshman or sophomore in college. I thought about going to medical school because, you could get wealthy that way. But I didn't really enjoy that sort of stuff. So I put my head down and kept going. In graduate school, as an undergraduate, I had a research project with a professor at UCLA who came from industry. And so, he had recently moved from industry to UCLA. And so I had a kind of unusual exposure to what industry was like. By the time I got to graduate school, everybody I knew in my class was dead set on being a professor. And, I remember asking a friend of mine, why do you want to be a professor? And he said, well, because I want to teach. And I said, but you're a TA now, and all you ever do is complain that you hate teaching. But it didn't affect him. So anyway, I had guessed I'd had some exposure to industry before, and liked what I saw.
And usually these doubts happens when you're an undergrad student. And I think from my perspective, when you go to grad school, especially after the master's degree, you start having a clear idea about if you want to work in industry or you want to work in either in academy, doing some research, or working for some research lab or some national lab, right?
Right. I wanted to do research, and what I saw was, I mean, like I said, the opportunities for my kind of career are much more limited today. But at the time I went to General Motors, they had decided they wanted a major research effort, fundamental research. So I got to GM, they said, here's your laboratory, go publish. And, I kind of felt that was better than my colleagues who were in universities who had to work hard to get funding, who were limited in what they could do research on by what they could get funding for, whereas GM was interested in pretty much almost everything. So it seemed like a good idea at the time.
Uh-huh. Now that we have some background on your experience, the first questions that comes to me is, what are the main reasons why they hired you?
So in an industry, if they hire you, they want you to solve a problem or to solve corporate problems. And they may have a very specific idea of what those problems are. Mm-hmm. They have no interest whatsoever, maybe even negative interest in you becoming famous, in you publishing. The idea that you might do something very different from what you're hired to do is not good in industry. Mm-hmm. They have a plan for you.
Okay. How is the success of your work measured, and how it is rewarded? Because if you are success, it is also rewarded.
In industry, you're successful if you help your company by solving a particular problem. It might also be that you help your company by becoming a subject area expert, so that other people in your company can come to you and ask for your advice or suggestions. So those are I think the measures of success. And the main way you're rewarded is by being promoted into management. So instead of people telling you what to do, you get to tell other people what to do. You have more responsibilities to the corporation rather than less. You are the one who's going to decide what other people do. You are given larger and larger groups to manage. And so you become, I think, more deeply involved in the company. So you tend to gravitate toward being more involved in corporate administration.
Mm-hmm. How are the research projects funded?
There's a couple of different models. There's central funding, and then there's external funding. And both of these are, I think, fairly common. It used to be that central funding was more common, but that was when there were big central research labs. If you get central funding, then you have someone in the corporation indicating what areas are of interest and what areas you're supposed to work in. And that's very similar to being a professor, where you have a granting agency, Department of Energy, Department of Defense, that tells you what they're interested in.
And now, moving forward, they already hired you. What are the difference in terms of collaboration? Let's say in an industry, how is the collaboration between the employee, the directors, and the subordinates?
I would say a collaboration is required because real world problems are just too complicated to be solved by one person. And since you're trying to solve a problem, you just have to have collaboration. In terms of collaborating with your superiors, if you're a young researcher in industry, you have to collaborate with senior people. Showing that you're independent may or may not be nice. It may be bad if you're seen as being not a team player. you're expected to work on a project that your supervisor has suggested to you if you're young. And if you are very successful in your project, then your supervisor will take credit for it to his or her supervisor. That's just the way it works. And you're rewarded because your supervisor is grateful to you for solving the problem. And so your supervisor will give you more resources for the next project.
Okay. Let's say you work for a longer time, let's say 10 years, 20 years. Does the career or does the job evolves in a different way?
So it seems to me, so keep in mind that I've never been a real professor. I was a visiting professor for a while. So my knowledge of academia is because most of my friends are academics, and so I talk to them. So let me put that caveat in. Not always, but often corporations decide that what they need is different from what they used to need. So when I was at Ford, I was working on fracture and cast aluminum, and that's because Ford was casting their own engine blocks, aluminum engine blocks. And then they sold all their aluminum casting plants one day. And so the way I found out about it was I came into work one day and somebody told me, I got to find a different thing to work on because Ford doesn't care about casting anymore. They're buying all their cast aluminum engine blocks. Well, at that point, I needed to find a new project. I chose lithium batteries to be my next project, which had absolutely nothing whatsoever to do with aluminum, at least on the surface. So my career took a big change in that way.
Do you have some experience before that working on lithium-ion batteries?
Yeah.
Have you worked in maybe materials or working performance, safety, something? Or you just came across with that topic and you say, okay, I'll work on it.
I was visiting a friend of mine at Caltech, and I was wandering down the halls, and there was an open door, and I walked in, and there was this professor that I knew, and I said, "Hey, what are you working on?" And he said, "Lithium batteries." And this was like 2004 or something like that. And I said, batteries hasn't changed in 100 years. He said, no, you just haven't heard about lithium batteries. So he made a pitch for me. And so then it got to be 2006, a few years later, and I had to find a new project. And I remembered that discussion. So I said, fine, I'll do lithium batteries. I didn't really know what a battery was. I mean, I'd had freshman chemistry, but I didn't know what a lithium battery was. So I just fell into, and I'd done that before. When I started at General Motors, I worked in combustion chemistry, and then I worked in wear-resistant coatings for gears. Then I worked in aerosol dynamics. I just worked in all sorts of different projects because GM or Ford, or whoever I was working with, changed their mind about what was interesting to them.
Yeah, but I feel like all the experience that you have in the different fields, like design, materials, at the end you can still apply it in the lithium-ion batteries.
So let me give you an example that's happening right as we speak. So in lithium batteries, one of the goals is to develop batteries that'll last for decades. So the car batteries that they're making now, maybe they'll last 5 or 10 or, well, more than 5, maybe 10 years, 12 years. Who knows? Because first lithium batteries went into vehicles in 2011 or 12. So those batteries are 10, 11 years old. Mm-hmm. So we don't really know. We don't have any experience. And that was just a tiny number. That was a Chevy Volt. Really, Tesla didn't get into making a lot of batteries until 2013, 14. Mm-hmm. So the oldest batteries in large scale are 7, 8 years old. So we don't know what happens to batteries after 15 or 20 years. So we don't have, so how do we design a battery for let's say the electric grid, which needs to last 20 years? How do we know that the batteries are going to last 20 years? We can look at the first year and say, well, there was only 1% degradation the first year. Mm-hmm. But how do we know that, in year 11, there's not going to be a catastrophic failure? And we don't really know. So, so right now I'm applying for funding for a project that's aimed at figuring out how do you quickly decide the long-term durability of a new battery technology. And nobody really knows. The standard thing done in the battery community is you raise the temperature of the battery, and that's known to kill off batteries very quickly. But the problem with that is that you induce particular failure modes when you raise the temperature, and those may not be the relevant failure modes after 15 years. You may be doing something different. So it turns out that gear manufacturers have a similar problem. Gears are meant to last forever, decades. And so if you come up with a new design for a gear or a new gear material, how do you figure out whether it's going to last 20 years? You can't just put them on test and wait 20 years. So the gear community has come up with some statistical approaches which allow you to get, at least statistically, a good handle on when these gears are going to fail, and you can do it very quickly. Let's say within a year, you get information that'll tell you whether these things are going to last 20 years. No one in the battery community has ever heard of that. Most communities have never heard of that sort of thing, but I know about it because I was working with gears. So my proposal is going to be, in large part, bringing that technology to the gear community. And nothing is better in your career than having a problem and discovering that problem was already solved in another field, and then you just copy and paste and you're a hero.
Yeah. I think that's one of the nice features that lithium-ion batteries, or actually energy storage systems, have. Like, it's an evolving technology. As you say, my PhD thesis was on aging and failure analysis of lithium-ion batteries. And sometimes I face the same problem. It's like I'm working with one battery that at the moment it was the best battery you could find in the market. But then 1 year later, you find that there are more batteries with more capacity and that last for a longer time. And let's say you test these new batteries. After 1 or 2 years, some people will start working with all solid state batteries. And when they optimize these batteries, somebody will say, oh, now let's move to sodium. Now let's move to magnesium.
Right.
It's a challenging problem, but it's also motivating because, there will be always something to investigate in this field.
That's what you hope. I mean, that's what I think. Solid state batteries is the new kid on the block, and
yes.
I mean, it's the timing is perfect because I was sort of getting tired of researching in liquid batteries. That had been done, and now we have a whole new area with new kinds of fields. I've done a lot of mechanics studies when I was looking mechanical failures when I was looking at gears or fracture in aluminum, and now a lot of that. Failure is relevant again in solid state batteries where it wasn't so relevant in liquid because you got fracture of these ceramics. And I mean, that's wonderful. I used to study fracture. And so anyway, that's great.
We're coming out to the top of the hour, so I will ask one final question. Many researchers perceive industry and academia as an immiscible liquids like oil and water. Academy is believed to produce only fundamental knowledge, and sometimes people think, oh, that's far away from reality. And then you look at industry, they produce technology which is intended to reach the market as soon as possible. My question here is there a possibility to create a bridge between these two sectors?
Yeah.
And most importantly, if you are a student or a researcher, that's the point where you would like to be, like being in contact with fundamentals, but at the same time, be in contact with the real world?
That's such an important question. It used to be that the bridge between industry and academia was the big central research labs. So the best ones were IBM and Bell Labs. Those are shadows. They barely exist anymore. And then every big company, Corning, General Motors, General Electric, every major company had a central research labs. And one of the jobs of the people in those central research labs was to be a conduit from universities to industry. So something new happens at a university, how is industry even supposed to find out about it? Well, they have people in their research labs who are attending conferences, who are publishing papers, who are buddies with the the professors, and so that was sort of a major function of the central research labs. The problem was and still is that if you're in a university, what you want is to make a step change. You want to make a major change, a major improvement. You want a Nature paper or a science paper that shows a new direction. That's what you care about. If you're in industry, you want a 2% improvement every year. You don't really want to work too much on big step changes because almost all of them fail. And I think one of the problems that the research labs had is that they were too academic. They were working too much on big changes, almost all of which didn't feed through, and not enough on how do you help the corporation make a 2% improvement every year. So with the demise of central research labs, that space is being filled from two sides. One is national labs. And so in the battery field, it's the mission of most of the major national labs to try and be that conduit between academia and industry. And more important, perhaps, is startups. And so universities, professors may have some very cool idea, and the way you try and get that into production is not through industry, but through making a startup. And the startup has to face the real world. Its job is no longer come up with a new idea. Its job is to figure out how to commercialize this thing. So that's sort of the new paradigm for being in the middle. The problem with that is that it was hard enough for people in central research labs to figure out what the corporation needed and how to get it into production. It's much more difficult for a startup to do that because at least if you're in a central research labs and you want to know what the transmission people do and what they need, you just go and talk to the transmission people and they'll tell you what they need and they'll give you help in setting up what you need. If you're at a startup and you want to help transmissions, you don't even know the names of the people to go to talk to. And if you did, they wouldn't talk to you because why would they tell you what they need? And so it's very hard. It's even harder to make that transition. And so often what will happen is companies will buy startups. So in the field of solid state batteries, the big, most successful startups have now gotten huge investments from corporations, and so that can work, but it means that there's a long sort of gestation period before you get to be big enough so you're noticed. So I would say if you want to do groundbreaking research and have it be have an impact on the real world, your best chance is with a startup. Now, of course, most startups fail, but that can be okay. In a field like batteries, there's so many jobs that you go to one startup, you do something, it fails, so you go across the street and there's another startup, and you work there, and so I think that's the best way as a student. If you want to have an impact, join a startup. Now, if you don't care about doing groundbreaking research and you want to have an impact, by all means go into industry, because then you're guaranteed to have an impact, because the only reason they're paying you is to have an impact. They don't care about Nature papers, and so they will tell you, here's what we need. We're hiring you because your training or your experience indicates you can solve this problem. You can help solve this problem. We have a group of 10 people who are working on, making a better thing. And what we're missing is the guy who can model it, or the guy who knows how to do postmortem diagnostics. So that's why we're hiring you. So if your real goal is to have an impact, by all means go to a company. If your goal is to do long-term fundamental research, you want industry, or you want academia, or maybe a national lab. And if your goal is to be in between, then you should go to a startup, I think.
I think that's the best way to close this talk.
Let me say one thing in conclusion, and that is that the most fun thing I do, maybe as I indicated earlier, is talking to students or young faculty or people just out in their starting their careers. So please contact me. I do this all the time. I mentor people at all stages in their early careers. My email address is sjharris@lbl.gov. S like Steve, J like Joel, Harris, sjharris@lbl.gov. Send me an email, or I'm on a couple of Slack channels. One is called Battery Modeling, and one is called Battery Street. So, get on those, or if you have trouble, I can get you on those. In fact, everybody who's listening to this should be on at least one or probably both of those to see what's going on in the field. And so anyway, contact me and I'd be happy to chat with you.
That brings us to the conclusion of this episode. Steve, thank you for taking the time to talk with us.
Okay, bye-bye.
Thank you very much to the audience for joining us, and please stay tuned for the next episode.